So, when we were, for example, using deadlocks, when we were using semaphores, we had like process one had code that said, let's say, we'll use Dijkstra's P function, P of X, and then let's say a P of Y. So this is a process that needs to get resource X and resource Y, and then it can start doing stuff. This could be a checking account, a savings account, or a printer and a disk drive, whatever you want, but it's some resource that is being shared. Then it can enter its critical section. And then it gives up resource X with a B, and it gives off resource Y. Okay, and then let's say process 2 asks for resource Y first. So this does have to, the resources have to be asked for out of order for this to occur. And then it asks for resource X. And then it begins its critical section. And then it gives up resource Y and it gives up resource X. So the developers of both of these codes believe they've done something safe. They're gathering their resources before they enter the critical section, and then they're giving them up when they're done. But we can have a scenario where the operating system allows process 1 to run, and during the call to this function, it times out. Now, if you just remember, this function, because it's a system call, it's part of the operating system, it's not part of your user code. If you time out in the middle of this function, it actually, the operating system will allow the completion of this function. It'll give enough time to at least the function finishes. But you don't necessarily get to start the next one. So if it times out between here, between this function call and this function call, then the other process, process 2, starts running. So process 1 acquired resource X, but never asked for resource Y. Now process 2 starts running. It asks for and successfully gets resource Y, and then it asks for resource X, and at this point it gets what we called last week block. Now the P function will actually interact with the operating system and move the process control block for process 2 off of the ready queue and onto the queue waiting for resource X. Okay. Now the operating system allows this process to start running again. And maybe what I'll do is I'll draw the operating system. Part of the operating system is OS as pointers coming out of it. One of these pointers is, I'll make this bigger, is the ready queue. So we might have the process control block for P1, which then is doubly linked. Last week, that will link to the process control block for P2. And maybe there's a third process running too that has nothing to do with this X and Y resources. Process 3. And then its next pointer comes back to here, and this one's previous pointer would then go to here. And then I think a few classes back we decided that we want to keep track of all the resources we currently have gathered. But it might not be a good idea to put that in a fixed block because we could have 0 resources and we could have 100 resources and we don't know how much room to allocate. So we'll generally make a pointer to a resource table for process P1. So this will be P1's resource table. And then maybe P2 has a resource table too, which dynamically changes in size. So this will be P2's resource table. Say resources. So we might record that process 1 has resource X in it, has acquired resource X, and at this point process 2 has acquired resource Y. We may also, although this would seem redundant, from the operating system's point of view, we may have an overall resource table. we'll call this the system resource table. This is all the resources for the system. So this might be, we might say resource X is currently allocated out to process 1, resource Y is currently allocated out to process 2. So you might see that this is redundant information, right? Here we're saying what resource, here we have a list of all the resources and who currently has them or if they're available. And here we have each process and a list of what resources they currently have. So you could get the information from either place, and you might think, well, I'm taking more time updating the operating system twice. But there might be an advantage to doing this. And since this is an operating system design question, there is no right answer. The more information you have, the better, but the longer it takes to keep it up to date. Okay. So the operating system now at this point, when process 2 asks for resource X, apparently process 2 would get moved because resource X is not available. Process 2 would get moved to the X queue. So somewhere in here is the X queue. And I'll do it in a different color. The green ones will say are stuck, and the operating system would have to reshape the ready queue like this. So now processes 1 and 3 can run only. Process 2 is now waiting for resource X to become free. Okay, so then process 3 runs for a while, has nothing to do with X and Y. It times out, and now process 1 runs. Process 1 picks up where it left off, and it asks for resource Y, which is currently allocated to process 2. We have it recorded 2 different ways. But more interestingly is that the semaphore value, Y, would currently be set to 0, meaning the resource is not available. So as a result of this function call, process 1 would get moved to the Y queue. Let me get the operating system chunk bigger. So there's a Y queue, and process 1 would then get moved to the Y queue, and then these would all be on. So now the only process that's ready at all is process 3. So the operating system has a ready queue, which points to process 3, and then process 3 is actually doubly linked to itself. That's the only one that's running. So now process 3 will be the only thing running. Process 1 is waiting for resource Y to become free so it can go back to the ready queue and start running again. Process 2 is waiting for X to become freed up so it can get moved back to the ready queue and start running again. And it turns out X and Y, process 1 and process 2, are waiting for each other to finish, and they'll never finish. So this situation is called a deadlock. And obviously it doesn't have to be just between 2 processes. 1 could be waiting for 2 to finish, and 2 could be waiting for 3 to finish, and then 3 could be waiting for 1 to finish. It doesn't have to be just 2. Got to be at least 2. One process by itself can never lock itself out. It has to be at least 2 different processes, but it can go off to infinity, as long as we have a loop in our collection of processes. Okay, so we want to define what conditions do we need for there to be a deadlock in our system. What would have to happen for there to be a deadlock? What properties would our operating system have to have before there's a possibility of a deadlock? Just because processes are running doesn't mean they definitely will deadlock, but they may deadlock. So the necessary conditions for a deadlock to possibly occur would be what? Well, our operating system would have to first of all have the concept of grabbing a resource and and therefore blocking other processes from having that resource. So we'll call that condition mutual exclusion. That means each process has the ability to exclude another one. They can mutually exclude each other. So if our operating system allows this to happen, and it'll be pretty tough to design a system that doesn't allow this. If you didn't allow this, then you couldn't have two processes operate on the same checking account or savings account. The only way you could ever operate on the checking account is go through this one program. So you couldn't have like ATMs all over the place. Okay, what else would have to happen in order for there to be a deadlock scenario occur? Any guesses? Like we're trying to, here's what our approach is. We don't want there to be deadlocks. So we'll consider creating a system that doesn't have that a deadlock could never occur. If we could fix our system, fine tune it so that a deadlock can never occur, then we can just let it run and know it'll never occur. But we have to define what has to happen in order for a deadlock to occur. So one of the problems we have, one of the scenarios to have a deadlock is you have to be able to hold one resource while waiting for another resource. If you can only hold one and therefore you were never allowed to ask for a second one, then we'd never deadlock either. So we need to have what they generally call a wait for. Our operating system would have to allow the wait for scenario. That means you're holding one resource while waiting for another one. The third condition our operating system would have to have for there to be a possibility of a deadlock occurring would be if the operating system had no preemption. Meaning, if your process had one or more resources under its control and asked for something else that was not available, if the operating system could come along and just say, okay, I'm undoing you, I'm going to force you to give up all your resources and you'll have to start over. If the operating system didn't have the ability to come in and do that, then the door is open again for there to be deadlock. And then the fourth condition would be a circular wait. Like I said, we need at least two processes to be in a loop with each other. Process 1 is waiting for process 2, and process 2 is waiting for process 3, and process 3 is waiting for process 1. So a cycle would have to be formed in order for there to be a deadlock occur. So if our operating system, if we go to design our operating system and we decide to allow all 4 of these conditions to be possible on our operating system, then the possibility that we could deadlock exists. Doesn't mean it's definitely going to happen, but there's a possibility that it could happen. So, some smaller systems, like some handheld devices that, I'm not talking about telephones, I'm not talking about cell phones, those will definitely have the possibility of deadlock. But smaller devices like, things that track deliveries, like you drop off so many cartons of soda in one place and then you mark that you've dropped them off. And smaller devices like that could actually decide they don't want to go into a deadlock. They could actually decide to not allow deadlocks to occur by picking one of these 4 necessary conditions for a deadlock and say, I don't want my system to allow one of those 4 to happen. And if you pick any one of those four and say, my system can't do that, then your system is guaranteed to not have a deadlock. So, how can we make a rule that, how can we have our operating system never allow mutual exclusion? It's pretty simple. We could just say we don't allow mutual exclusion. There are no semaphores, there's no way any process could ever have mutual exclusion of a resource. But if you think about it, that's limiting what you have the ability to do. So denying, so first of all, we're talking about the topic of deadlock, avoidance. So with deadlock avoidance, one choice is don't allow mutual exclusion. Don't allow mutexes. If you don't allow mutexes, you'll never hit a deadlock. Nobody can never grab a resource. There'll never be a deadlock. But there's so many things we now would not be able to do. We couldn't use a printer. We couldn't use a disk drive. We couldn't have any shared memory, like a checking account, a savings account. We'd be very, very limited in what we could do, but we would solve the problem. How could we, so this is very unrealistic. Okay. The second one is don't allow wait for. How could we implement an operating system that doesn't allow you to hold one resource while waiting for another? So I guess, so the operating system would have code in it that says something like, if you have, we had the blocks before, so we can keep track of what resources you have and don't have. If you have a couple of resources and then you ask for something that's not available, what could the operating system make that process do? If we decided we're not going to allow this to occur on our operating system, what's something we could do? What we could do is say, if you ask for a resource and you are denied, you have to give up all the resources you've acquired so far. Okay, so really there's probably two ways. One would be force giving up all resources, all acquired resources. If you're ever denied. So, any comment about implementing this, if you implement this on your operating system, which basically says if a process needs 4 resources to proceed, it gets the first 3, asks for the 4th one, and the operating system says, well, that one's not available. The operating system forces it to give up all three resources and kind of start over. This will guarantee no deadlock, right? Because no process will ever hold something indefinitely. They'll either finish or they'll be asking for something that can't get, and as soon as they ask for something they can't get, I guess we'd have to change the P or the B function, the P one. We'd have to change that one to say if the resource you're looking for is not available, then we'll look at your table to see what you currently hold, and we'll force you to give all those up. We'll do what is equivalent to a V function on everything you currently hold, and then you have to start over again. We'll have to put your program counter back to the point where you start asking for the resources again. But it's doable. It's something we could do. We could design our operating system to not allow this wait for condition, where you hold one resource and then you're waiting for another one. One way to do that, so I'll do like 2 methods. Method A is force the process to give up all of its resources if it ever asks for something that it can't get, and then start over. So this will definitely get rid of deadlocks, but is there some comment, you know, is there something you like or don't like about this?
Probably never get anything done.
Yeah, I mean, you probably will eventually get things done, but a process may have to gather up its resources. That's going to take time, right? Just running all those P functions. You gather up your resources, and then you hit one, boom, oh, now I have to give everything up and start over again. Yeah, so it would end up taking a lot more time to get the work done. Could be considerably more time. Another one might be a little bit of a cleanup of it is you tell, but you're going to end up with the same problem. Force all processes to acquire all resources first. So if you're, yes, so, and if you don't get them all, this is kind of the same as the last one. If you don't get them all, then you give them all up and start over again. But it's just instead of you having a 1 hour process where you get resources kind of a few at the beginning, a few at the middle, a few at the end, and then get stuck and you have to start all over, why don't you ask for the resources all at the very beginning? And either you get them all or you don't, and if you don't, you give them all up and you start over again. You loop around to the ready queue and try again later. This is like maybe a slight improvement over the last one, but there's actually a downside. Suppose you have a 6 hour process to do, and you need one resource for the first hour and another resource for the 6th hour. This thing forces you to get both resources at the beginning, and you don't really need the second resource till 5 hours later. But this method, if we impose this on our system, would force us to get resources we don't need at the moment. Okay, what if we wanted to deny the no preemption rule? So no preemption means if you have a resource and you're hanging on to it and waiting, the operating system cannot come in and force you to free it up. Well, one way to deny it is to allow preemption. So preemption is where the operating system comes in and says, all right, you've been stuck too long, I'm freeing up all your resources, I'm kicking you out, and you got to start over. So we can allow that, and that will guarantee no deadlocks. But then the operating system would have to have some mechanism that kind of is monitoring what's going on, and then notices that there's a deadlock. Then, since it's a group of processes in a deadlock, you only have to kill one of them. You don't have to kill them all. You can kill one and then the cycle goes away. So we might have an algorithm to choose which one to kill. So this one's kind of doable, and it's probably what we'll focus mostly on. It's probably the most sensible one, but it involves some work. The fourth way is to not allow a circular wait. How could we not allow a circular wait? Remember when I wrote the example? I wrote the example before. I said we had process 1 asked for X and then asked for Y, and process 2 asked for Y and then asked for X. What if process 2 asks for X first and Y second? In other words, in the same order as Y. I'm sorry, as process 2. Suppose it asks for X first and Y second. Could this have deadlocked? Or did I have to flip the X and the Y to then have the deadlock scenario possible to have? If they both ask for X first, you know, they, like these two programmers are talking to each other and said, you know, make sure you ask for X first before you ask for Y. Could they have a deadlock? Could these two processes ever deadlock? So the answer is no, because whoever gets X will be able to go all the way till they finish, and the first one who doesn't get X will get stuck asking for X. So they'll never have the scenario where they have one resource and then is waiting for the other. So we can deny the circular wait scenario. What would we have, what rule would we have to put in place in our operating system to make sure that of all the processes, could be hundreds and thousands of processes, and it could be thousands of resources, what rule would we have to put in place to guarantee there'll never be process 1 is waiting for 2, and 2 is waiting for 6, and 6 is waiting for 9, and 9 is waiting for 1, that we could never have a loop? We could have a rule on our operating system that says for every resource that there is, we're going to number them sequentially, and when you ask for them, make sure you ask for them in number order. So, but then, you know, if it's a very limited system, like some little handheld device keeping track of how many sodas you delivered, you might be able to do this. But if it's like, there's disk drives and printers and fax machines and files on printers and then account values in the files, you'd have to consider every possible resource that we could share and assign a number to it. And every time your computer adds a new resource, it has to be assigned the next available number. And then we'd have to tell every programmer, we'd have to print a chart and put it on the wall or something for everyone to see, and we'd have to hope that everybody asks for resources in a particular order. If we did that, then we can be guaranteed, again, there's no deadlock. So it's possible to create a system, create an operating system that is deadlock free. But it's not very realistic, right? I mean, we can't get rid of mutual exclusion. That'll just stop us from doing so much stuff. For most systems, numbering every resource and telling everybody, make sure you ask for those resources in a particular order, it's not very realistic. The getting rid of the wait for condition, it's possible, but like you were saying, we're not going to get a lot of work done. We're going to spend a lot of time gathering resources and then being told, all right, give them up and start over, and that'll happen a lot. So we'll lose a lot of time. It's doable, but we'll lose a lot of time. The no preemption, meaning the operating system can't jump in every once in a while and say, all right, I've noticed, and we're hoping deadlocks don't happen too often, but if there is a deadlock situation, the operating system could jump in and pick one of the processes and then force it to start over, give up all its resources. So let's focus on that approach. In other words, as far as deadlock detection goes, in other words, let's say we've made as operating systems designers, we've made a decision to allow the possibility of deadlocks to happen. You know, it's like lightning striking. It could happen. It's rare, but it could happen. But if we decided to allow it to possibly happen, then we need to look into deadlock detection. You know what? Before we go to deadlock detection, let me go over an example of we're still on the topic of avoiding deadlocks. I just want to introduce the idea of having a pool of resources. And let's take a look at an example like this. This is a topic that is called, it's the same guy at Baxter we talked about when it comes to semaphores. So this is called Dijkstra's banker's algorithm. So suppose we had process A, okay, process B and C, and we had, there's one resource, and we're just going to take this idea and expand it to multiple resources. But the total need the total access. Total access, total needed. And then remaining need. Okay, so this is process 2 and process B and process C. Okay, so let's say process 1. So we have a pool of 12 of some identical resources. Could be 12 printers, but just 12 things that are exactly identical on our entire operating system. And process A, B, and C need a few of them during their processing to finish. So we know process A, B, and C have been compiled, so we can see at its most neediest point, or its high water mark, how many it would need totally. So let's say the total needs for process A are 4 of them. The process B would be 6 of them, and process C would be 8 of them. So obviously, if we had 4 plus 6 plus 8, if we had 18 of them, there's no problem for these 3 processes to run. They could run, gather up whatever they need, and finish their job. But suppose we only had 12 of them, a total of 12. If we let these 3 processes run and let the operating system allow each one of them to have a certain time, there's a possibility, but it's not definite. There's a possibility that this might deadlock. So they're not asking for all the resources at once. So process A doesn't say, I need 4, otherwise I'm not going any further. And then process B says, I need 6, and C says 8. Then we'd have a pretty high probability of deadlock. But process 1 might need 1 or 2 at the beginning, then it might give a few up, then it might need 4, then give them up, and then need 1 more, and then can finish. But at its worst time, at least at one point, it will need 4 at once. And same is true, B needs 6 and C needs 8. So let's say and we have a total of 12. Would you say that this will definitely deadlock, may deadlock, or is there some way we can guarantee it would never deadlock? And we as the operating system, we can suspend some of the requests. If somebody makes a request, we can say, wait, you'll have to wait. So will it definitely deadlock? Does it seem like a system that would definitely deadlock? Worst case scenario, there might be a request for 18 resources and we only have 12. But could there ever come a point where A is waiting for B and B is waiting for C and C is waiting for A and they'll never finish? Well, okay, so first of all, the statement it will definitely deadlock is not true. Because A could use all 4 resources and be done and get out of the system, and then let's say C used all 8, finished its work and gave them up. Now we have a need for 10 more and we have 12. So the statement it will definitely deadlock is not true. It may deadlock if more than 12 are being requested. We'd actually have to, and I think this is one of the homework questions, we'd actually have to have a request of 15 of them. Because all 12 would have to be taken plus at least, each process is requesting at least 1 more, so therefore they're stuck. So there's kind of a minimum of how many requests would have to be before we have a deadlock. But let's say at one particular point in time, Process A currently has 1, process B currently has 4, process C currently has 5. That would mean, 10 have been allocated out, so available would be 2 more. The operating system has 2 more to give out. And so what would the remaining need of this be? So the remaining would be this number minus this number. So the remaining needs would be 3, 2, and 3. So now, if we're the operating system, now again, this is just, there's one resource type, but we have 12 identical copies of it. And these processes will take any one of the 12. They're all identical to the process. The operating system controls 2 more. There's 2 more that are available to give out, and then we have no more to give out. Is it possible for the operating system to guarantee all of these jobs finish, all of these processes finish? So, did anyone say no or yes? No? Well, okay, so what may happen, so A, B, and C are going to be running, and the next thing that may happen is A may request 1. Well, if we grant that request, we'll be in this situation. It will have 2, it'll need 2 more, and we'll only have 1 left to give out. Now, can we be guaranteed that one of these 3 will finish, and then give all its resources back? At this point, we're in trouble because the very next thing that A might do is ask for 2 more. And then B might ask for 2 more, and C might ask for 3 more, and then we're stuck. So this would be a bad situation to be in, but let's go back to the way we were. We have 2 to give out. We have 2 more to give out. And it looks like process B will never ask for more than 2 more. So at this point we can say, as far as process A and C are concerned, if they ask for any more resources, from this point on we're going to temporarily deny them. The only thing we're granting to process, the only resources we'll be granting will be going to process B. Because B we know we can get finished. If we grant the last 2 to B, it will need no more. Oh, sorry, this will become 6, and now we know it, just give it some time, it will finish. And then once it finishes, it will give all 6 resources back to us. And we'll have 6 here to give out. And then A and C only need 3 more in the worst case scenario, so we'd be fine then. So this is what's referred to as being in a safe state. So what we're really doing is we're granting resources out. This is now for any resource, and we're going to have a number of resources in our operating system where they're identical, so we have a collection of them that we can give out. We'll give them out as long as the operating system considers itself in a safe state. And the definition of a safe state is we have enough resources available to guarantee that at least one process can definitely finish. But that's even that's not enough to say you're in a safe state. The one that finishes then returns its resources to our pool. That would have to give us enough resources for at least one other one other process to finish, which would then return more. We'd eventually have a path that will let us have all processes eventually finished. And then there was an example of, obviously we can expand this to multiple resources. And there was there's an example in the notes that goes like this. So we have process A, B, and C, and we have resource 1, and the amount we have is 1, the total need is 4, which means we could be asking for as much as 3 more. Resource 2, and realize we could just do resource 2, 3, 4, 5, different types of resources. We would have 4, 6, 2, 5, 8, and 3, which I think are the same numbers as the first example. Now we're just adding a second resource. 2, 6, 4, 2, 4, 2, 1, 2, 1. And the total available for each, so this is now resource 1 and resource 2. So this is the amount the operating system has left. Let's say we have 2 left and 1 left. So resource 1 is the same as the example we just did before. We're just now adding a second resource, which is also a pool. So how many are there? There would be two out right now, 4, 5 are out, plus 1 in reserve. So there's a total of 6 of resource 2, a total of 12 of resource 1, like in the last example. And now we ask ourselves, are we in a safe state? Can the operating system be guaranteed? Now, it's going to start being stingy as far as giving out resources, but can it be stingy and be guaranteed that all 3 processes, A, B, and C, will eventually finish? So, is there any process that we can definitely guarantee will finish? Well, like the last example, we can only guarantee B will finish, because B only needs 2 more resources and we have 2 to give out. So if we say from this moment on I'm only satisfying B's request because we're a little tight on resource 1, can we guarantee that process B will finish? And in this case, we are not in a safe state, because even if the operating system said temporarily I'm only satisfying process B, we could satisfy their request for resource 1, but we don't have enough available to satisfy their request for resource 2. So they might ask for the last 2 of resource 1, and we can give that to them. But if the next thing that happened, if A or C doesn't start freeing up resource 2, we may never have enough resource 2 to satisfy B's need, and B may run into a deadlock. And then A and C will be needing B to finish, and it will never finish. So you can see we can take the concept of the last example and then just keep adding more resources, and you have to be able to, in order for the operating system to be in a safe state, there has to be enough reserve resources for all the resources to guarantee that at least one process could definitely finish. And in addition to that, when that one finishes, it must return enough resources that we can then get more finished and eventually get them all done. So we only give out resources. We can give them out as they're being requested, but as long as the state that the operating system is in remains a safe state. Okay, so this Banker's algorithm is a guarantee of not going into a deadlock. But now there's more checking to the P function before we decide whether to give out the resource or make it wait. Now, if we just decide to let the operating system run freely, from time to time the system will go into a deadlock state. We need to figure out a mechanism to detect it and break out of it. So there's the concept of a resource allocation graph. So if we have process A, process B, and process C, and then we have a pool of resources. We have resource 1, and let's say there's 2 of them. It doesn't have to be just 1. Many resources, there's only 1 of them that exists on the whole system. And resource 2, let's say there's 3 of them. We might find ourselves in a position where process A is requesting, so an arrow for a graph, remember from your graph theory or graph algorithms classes, this is a directed graph. Process A is requesting resource 1, but at the present moment resource one has been one of them has been allocated to process 2, and one of them has been allocated to process, sorry, not to B, and process C. And then one of resource 2 has been allocated to process A, one has been allocated to process B, and one of resource 2 has been allocated to process C. And let's say process B is also requesting resource 2, but that request is currently unsatisfied. And process C is currently not asking for any resources. So, we would be able to take the information in the operating system, in those process control blocks, those fields that say what resources are allocated to which processes, and we would be able to build this graph. Now, what would we be looking for to answer the question yes or no, is there a deadlock? Well, we know from the circular weight issue, we would know that we would need process. Every arc in this graph goes from the left side to the right side. So a process can't be asking for another process. A process can only be asking for a resource, and resource can only be assigned to processes. So the arrows go back and forth, but in order for there to be a loop, we would need something like A is requesting resource 1, which is not available. Resource 1 has been assigned to B. B is requesting 2, which is not available, and resource 2 has been assigned back to 1. So there would have to be a loop somewhere in this graph. If there's no loop, we are guaranteed there's no deadlock. Everybody's running fine, just give them more time and hopefully they'll finish. If there is a loop, if there's a loop and these resources they're pooled, each resource only has one of each type, then there definitely is a deadlock. If they are a pool of resources, then it's kind of like the Dijkstra's Banker's algorithm. There might be a way that it could finish, or there might not be. But we would need an algorithm that detects a cycle. We'd need an algorithm that builds this graph. We would then need an algorithm that checks for a cycle in the graph. And then if they are unpooled, a cycle means yes, there's a deadlock, and a no cycle means no, there's no deadlock. If they're pooled, then there is a possibility that there could be a cycle and yet no deadlock. So for example, if C finished, that would free up resource B, and then B would finish, and then A could finish, in this particular case. So that ends up being a question that goes to your, like, CS 512, the algorithms class, where you build graphs, directed graphs, and then run algorithms on them that tell you yes or no if there is a cycle or not. So the operating system would have to, from time to time, because if there's no deadlock right now, there might be one 2 minutes from now. So it would have to, from time to time, rebuild this graph and then run the algorithm to see if there's a cycle. So there'd have to be a separate process running, just constantly building this graph and checking. Actually, it wouldn't have to keep constantly building it. It could just update it every time a resource is added or deleted, and then rerun the algorithm and see if there's a cycle.